The engine controls are located on the control stand and the overhead panel. On the control stand are the thrust levers for forward and reverse thrust, in addition to the fuel control switches. The fuel control switches are used to start and stop the engine. The switches control the spar and engine fuel valves and also are part of the circuitry for the engine ignition. You would watch the fuel valve lights to ensure proper valve operation during engine start and shutdown. If an engine fire is detected or during a fire system test, the red lights in these switches will come on. The thrust levers move fore and aft to provide a thrust request to the EEC. Forward thrust can be manually set, but is more often set by the auto throttles. At any time, the pilot can override the auto throttles to manually set power. With the thrust levers at forward idle and the aircraft on the ground, the reverse levers may be raised to manually select reverse thrust. Thrust reverse cannot be selected unless the aircraft is on the ground. On the next few frames, we'll describe the operation of the thrust reference limit modes and reference values that are provided. This information is displayed on the ICAS, so the pilot is aware of the current thrust limit mode and the target thrust value. The target thrust value provides an auto throttle target or limit when the auto throttles are engaged. Normally, the Thrust Management Computer, or TMC, calculates a reference N1 according to the current thrust limit mode. This information is displayed as a target bug and also provides a green digital readout above the N1 gauges. The N1 limit mode may be selected on the Thrust Mode Selector panel, TMSP, or it may be selected by the Flight Management Computer, FMC. In either event, the thrust reference mode appears above the N1 gauges. The available thrust limit modes are shown on this frame. Consult your flight manual for which modes are used by your airline and how to select them. When VNAV is engaged, the FMC controls thrust automatically to meet thrust requirements for the active vertical flight path. In VNAV, the TMC receives thrust settings from the FMC and the N1 bugs display in magenta. In this case, the N1 bugs reference a target N1 for the VNAV mode, which may not correlate with the thrust mode limit value that displays in green. The N1 bugs can also be set manually, although you will not often use this feature. You should know that the auto throttles do not respond to these manually set limits. To manually set the N1 bug, pull up on the Manual Thrust Reference Set knob, and MAN appears above the N1 gauges, and the N1 bugs slew to a default setting. The outer knob is normally in the both position, so both bugs are set the same. With the inner knob pulled up, the N1 bugs are set by rotating the control knob. If you want to control only one bug, you can rotate the outer knob to select the left or right bug for selection prior to rotating the inner knob. Finally, remember that the auto throttles are in no way associated with manually set N1 bugs. The auto throttles are not normally used if the bugs have been manually set. Before we leave a discussion on the reference N1 and N1 bugs, you should know that these items blank when the reversers are fully deployed. Click the reverse lever to demonstrate the change of displays during reverse thrust. We will now provide a brief overview of setting reduced power for takeoff and climb. You must check your company procedures for use of reduced power. For takeoff, the use of reduced thrust is normally prohibited for the conditions shown here. Please keep in mind that further restrictions may be provided for certain dispatch deviation procedure, DDP, or configuration deviation list, CDL conditions. The derated takeoff mode can be selected by dialing the assumed temperature on the TMSP assumed temperature selector or by entering the assumed temperature on the control display unit. By the way, it is more common to use method number 2. Note the CDU page title shown here for entry of the derated temperature during pre-flight. With either entry method, the assumed temperature appears on ICAS and on the CDU page. Note, the system will not accept an assumed temperature that would allow the thrust to be reduced more than 25%. During takeoff, after the auto throttles are engaged, the thrust levers will advance to set the target thrust. Power must be properly set by 60 knots. You must verify the power is set and be prepared to manually adjust the setting. The auto throttles will engage the throttle hold mode at 80 knots. This indicates that the throttle servo is inactive, so the pilot can manually move the thrust levers without restriction. After takeoff, if the auto throttles are engaged, selection of the highlighted buttons shown on this MCP above 400 feet radio altitude will automatically engage the climb mode. The system is capable of providing 2 reduced climb thrust modes with the selection of the 1 or 2 mode switches on TMSP. With the airplane in flight in the climb reference mode, pushing the 1 or 2 switch changes the climb thrust reference from climb to climb 1 or climb 2 as appropriate. Similarly, you can reselect full climb power by pressing the 1 or 2 switch to turn off the reduced climb power. You can pre-select the reduced climb power so it will automatically engage rather than full climb power. These are some examples of pre-selected derated climb power displays. Takeoff is for full power takeoff. D-takeoff is for reduced power takeoff. The white numbers 1 or 2 indicate the pre-selected reduced climb thrust mode that will engage when climb thrust is active. To review, normally you will select Flight Level Change or VNAV after takeoff, and this action will change the thrust reference from a takeoff mode to a climb mode. If your aircraft does not have this option, you'll need to make the climb mode selection on the TMSP. Make sure you check your company procedures on use of reduced takeoff and climb thrust. The EEC's switches and start panel are located as shown. We'll now describe the operation of the EECs. The thrust system consists of a dual-channel, full-authority electronic engine control unit, or EEC. The EEC sets power and provides engine limit protection, like an engine governor. Since the EEC actually sets the power, a failure of an EEC will cause the engine to fail. For reliability reasons, redundancy is built into the EECs. Each EEC is self-powered when the respective engine is operating. The power is provided by a dedicated permanent magnetic alternator, or PMA. The EEC continuously computes the maximum thrust limit, which is displayed as an amber line on the inner arc of the N1 display. You always have available thrust to this limit if the thrust levers are pushed full forward. The engines are constantly protected from overboost and overspeed by this limit. Each EEC switch is usually guarded in the normal position. The norm light is on and the alt light is off. You will check these switches on your pre-flight and normally have no other interaction with the EEC. Since the EEC calculates the thrust, it can graphically display the thrust result of a thrust lever movement prior to the change of the engine thrust. Therefore, during rapid thrust lever movements, the difference between the current N1 and the commanded N1 is displayed with a white command sector. Click the thrust lever a few times to watch this display. The ICAS advisory message, left or right engine control, displays when faults are detected in the engine control systems. This message is designed to prevent dispatch with these faults. If you are already en route when this failure occurs, the alternate mode will operate. The alternate mode still has a dual channel system, providing redundancy to the engine fuel controls. The alternate mode is engaged automatically if the normal mode has failed, or manually by selecting the guarded switch to the released position. In any event, when alternate is engaged, the alternate light illuminates, and the ICAS advisory message, left or right, engine EEC mode is displayed. Automatic reversion to the alternate mode results in the soft alternate mode. Manual selection of the alternate mode results in the hard alternate mode. There is no real difference to the pilot, except that when soft alternate engages, there should be no noticeable change of thrust. This may not be the case with engagement of hard alternate, which may cause the thrust to set the commanded N1. In alternate, thrust is controlled in a manner similar to conventional fuel controls. Since the constant N1 setting produces different thrust levels at different ambient conditions during climb and descent, the thrust levers will need to be adjusted to maintain constant thrust in this alternate control mode. In alternate, automatic thrust limit protection is not available, and thrust overboost can occur at the full forward thrust lever positions. However, if the thrust lever position will command an N1 greater than the maximum rated thrust, max N1, the ICAS caution message, left or right, engine limit protection, will display. In either norm or alternate, the EEC provides N1 and N2 red line overspeed protection. so that if N1 or N2 approaches overspeed, the EEC commands reduced fuel flow. In this case, the ICAS advisory message, left or right engine RPM limit displays to indicate N1 or N2 is at the red line limit. Note, the EEC never provides EGT over temperature protection in either mode. The minimum idle or approach idle speeds are selected when the thrust levers are set at forward idle. The EEC selects these idle speeds automatically. Minimum idle operates for ground operations and all phases of flight, except approach and landing. Approach idle is selected whenever a higher idle setting is required, such as for landing when a go-around may be required. Rotating the engine start selectors to continuous manually selects approach idle. This feature spools up the idle speed in the event you have selected continuous ignition for meteorological reasons. Basically, the approach idle mode causes the engine to operate at a more reliable and stable idle speed to penetrate unstable weather conditions. If an engine fails to go through the approach idle mode when it should, the ICAS advisory message, left or right engine low idle, displays. An additional ICAS advisory of idle disagree indicates the engines are at different idle settings. Possibly an engine has failed to increase to approach idle, or an engine has failed to return to minimum idle. In this situation, to ensure the idle is proper for performance requirements, the pilot should advance the thrust lever on the engine with the lower RPM to match the good engine. This completes our description of engine thrust control. Now for the questions.